Welcome to Deep Science Sleep. Close your eyes for a moment and imagine yourself floating weightlessly in a vast, dark ocean of space. The stars around you shimmer softly, distant and eternal, their light traveling for millions of years just to reach this moment where you rest. You're suspended here, perfectly still, perfectly safe, in a place where the usual rush and pressure of time seems to dissolve like mist in the morning sun. Your breathing slows naturally, deeply, as you let yourself drift in this infinite cosmic sea. There's no hurry here, no deadlines, no ticking clocks demanding your attention. Just you, floating peacefully, ready to explore one of the universe's most fascinating mysteries in the gentlest, most soothing way possible. As you settle into this comfortable darkness, imagine that each breath you take is a wave lapping at the shore of consciousness, slowly washing away the day's tensions, leaving only curiosity and calm wonder. Tonight, we're going to journey through time itself, but not in the frantic way you might expect. We'll move slowly, thoughtfully, letting each idea settle like snow on a quiet winter evening. So take another deep breath, release it slowly, and let's begin our peaceful exploration of what time really is, according to the beautiful, elegant truths of physics. The fundamental nature of time. When you think about time, what comes to mind? Perhaps you picture a clock, its hands sweeping endlessly around a numbered face. Maybe you imagine a calendar, pages turning with the seasons. Or perhaps you feel time as a sensation, the gentle pull of moments sliding from future through present into past, like water flowing eternally downstream. But what if I told you that time, this thing we feel so intimately connected to every second of our existence, is far stranger and more wonderful than any of these everyday images suggest? In the realm of physics, time isn't simply what keeps everything from happening at once. As the old joke goes, time is woven into the very fabric of reality itself, as fundamental to the universe as space itself. When the mathematician Hermann Minkowski presented his revolutionary interpretation of Einstein's special relativity in 1908, he offered a vision of time that was both radical and strangely comforting. He described space-time as a single, unified entity where 3 dimensions of space and 1 dimension of time fuse together into a 4-dimensional continuum. Imagine this for a moment. As you lie here in the darkness, your body relaxed and your mind open. You're not just existing in space, occupying some particular spot in a 3-dimensional grid. You're existing in space-time, extended not just through width, height, and depth, but through time itself. This is a deeply peaceful thought if you let it settle into your awareness. Every moment of your existence, every breath you've ever taken, every sunrise you've witnessed, every kind word you've spoken, all of these form a continuous thread through space-time. Your life isn't a series of disconnected instants flickering in and out of existence like frames in a film. It's a coherent, beautiful pathway through 4-dimensional reality, as real and solid in its own way as the path your feet might trace across a sandy beach. Take a moment to truly contemplate this revolutionary idea. In the 3 familiar dimensions of space, you can move freely in any direction you choose. You can walk north or south, climb up a ladder or descend into a basement, reach east or west with your arms. Each of these dimensions is independent, giving you freedom to navigate the spatial world around you. But time, this 4th dimension, behaves differently from its 3 spatial cousins in crucial ways that make it unique and special. First, while you experience three spatial dimensions symmetrically, able to move back and forth along any of them with relative ease, time presents itself to your consciousness as having a definite direction. You move forward through time continuously, inexorably, unable to reverse course or stand still. This asymmetry between time and space is one of the deep puzzles that physicists grapple with, because at the level of fundamental physics, at the level of particles and forces, most laws are actually time-symmetric. They work equally well whether time flows forward or backward. Consider a simple example from everyday physics. If you watched a video of billiard balls colliding on a pool table, and someone showed you that video running backward, you'd have a hard time definitively proving which direction was the real forward direction of time just from the physics of the collisions. The laws governing how the balls exchange momentum and energy work the same way in both temporal directions. And yet, if you added friction to the mix, if you included the gradual slowing of the balls as they roll across felt, then suddenly you could tell which direction time was flowing. The balls gather speed when played backward, which violates our experience and understanding of how friction works. This distinction hints at something profound. The microscopic laws of physics, the equations describing individual particles and their interactions, are largely time-symmetric. But the macroscopic world we experience, the world of friction and heat and irreversible processes, displays a clear arrow of time pointing from past toward future. This emergence of time's direction from fundamentally time-symmetric laws is one of physics' beautiful mysteries. One we'll explore more deeply as our journey continues. Another way time differs from space is in how we measure and experience it. Distance in space is something you can traverse in either direction at various speeds. You can walk slowly or run quickly. You can turn around and retrace your path. You have agency and control over your motion through space, at least in normal circumstances. But your motion through time feels different, doesn't it? You move through time at what feels like a fixed rate, 1 second per second, unable to speed up or slow down at will, unable to reverse direction no matter how much you might wish to visit yesterday again or preview tomorrow. Yet relativity, as we'll discover, reveals that this sense of moving through time at a fixed universal rate is an illusion. Different observers move through time at different rates depending on their velocity and gravitational environment. The rigid, absolute time of Newton, ticking away uniformly for all observers throughout the universe, doesn't exist. In its place, Einstein gave us a more subtle and strange reality where each observer has their own proper time, their own personal clock, and these clocks run at different rates depending on motion and gravity. Space-time, this four-dimensional fusion that Minkowski described, isn't just a mathematical abstraction useful for calculations. It represents something deep and real about the universe's structure. When you look at a distant star, you're not just seeing across space to where that star is located. You're looking across space-time, seeing the star as it was when the light you're detecting began its journey, perhaps years or even millions of years ago. Every photon of starlight carries information not just about a position in space, but about a moment in time, a point in space-time where it was emitted. This interweaving of space and time has profound implications. It means that the universe's history isn't separate from its spatial structure. Space and time together form the stage on which all events occur, and this stage is dynamic, responsive to the matter and energy it contains. Mass and energy curve space-time, and this curvature is what we experience as gravity. The Earth orbits the Sun not because some force reaches across empty space to pull on it, but because the Sun's mass curves the surrounding spacetime, and the Earth follows the straightest possible path through this curved four-dimensional geometry. Imagine, as you lie here relaxed and comfortable, trying to visualize 4 dimensions at once. It's not easy, is it? Our brains evolved to navigate 3 spatial dimensions, to judge distances and heights, to throw projectiles and catch prey, to build shelters and avoid obstacles. We're not equipped with intuitive 4-dimensional visualization. But mathematically, 4-dimensional spacetime is perfectly well-defined, precisely describable through equations that have been tested countless times and found accurate every time. You can't visualize 4 dimensions directly, but you can understand them through analogy. Imagine a being that lived in a 2-dimensional universe, confined to a flat surface like a sheet of paper. Such a being couldn't directly visualize our 3-dimensional world. To them, a sphere passing through their 2-dimensional plane would appear as a circle that grows from a point, expands to a maximum size, then shrinks back to a point and disappears. They would experience only 2-dimensional slices of the 3-dimensional object, unable to perceive the whole sphere at once. Similarly, you experience only 3-dimensional slices of 4-dimensional spacetime. At each moment of your consciousness, you're aware of a 3-dimensional space at what you call now. The next moment, you're aware of another 3-dimensional slice at a slightly later now. Your consciousness slides through spacetime like that 2-dimensional being would slide across a 3-dimensional object, experiencing one cross-section at a time, building up a sense of temporal progression from the succession of spatial slices. This is why your experience of time feels like flow, like motion through a dimension, even though from a 4-dimensional perspective, nothing is actually moving. Your entire world line, your complete 4-dimensional existence from birth to death, exists as a static structure in spacetime. But your consciousness is a process that unfolds along this world line, experiencing each moment sequentially, creating the powerful illusion of time flowing, of the present moment advancing inexorably from past toward future. Minkowski himself captured this revolutionary idea in words that still echo through physics today. Henceforth, space for itself, and time for itself shall completely reduce to a mere shadow, and only some sort of union of the two shall preserve independence. What he meant is that space and time, which we experience as separate things in our daily lives, are actually 2 aspects of a single underlying reality. They're like 2 sides of the same coin, inseparable and interdependent. Think about it this way as you relax deeper into stillness. When you see a shooting star streak across the night sky, you're not just seeing something move through space. You're witnessing a 4-dimensional event in space-time, where the meteor's path through 3 spatial dimensions is inextricably linked with its progression through time. The shooting star doesn't just occupy different positions in space at different times. Instead, it creates a single, unified structure in spacetime called a world line, a concept we'll return to later in our gentle journey. But time has another fundamental characteristic that makes it unique among dimensions, something that sets it apart from the 3 dimensions of space we can move through so freely. While we can walk forward or backward, turn left or right, climb up or descend down through space with relative ease, time seems to have a direction, an arrow that points inexorably from past toward future. We call this the arrow of time, and understanding why it points the way it does requires us to explore one of the most fundamental principles in all of physics: the second law of thermodynamics and its relationship to entropy. Entropy is often described as disorder, but that's not quite right, not quite precise enough to capture what entropy really means. Instead, think of entropy as a measure of possibility, of how many different microscopic arrangements could give rise to the same macroscopic state you observe. Imagine a pristine bedroom, everything in its perfect place, books alphabetized on shelves, clothes folded neatly in drawers, dust completely absent from every surface. This highly ordered state corresponds to relatively low entropy because there are only a few specific arrangements of all those molecules and objects that would produce such organization. Now imagine that same bedroom after months of neglect, clothes scattered across the floor, books in random stacks, dust coating every surface. This disordered state corresponds to much higher entropy because there are countless different arrangements of molecules and objects that would all look equally messy to your eye. The second law of thermodynamics tells us that in any closed system, entropy tends to increase over time. The organized bedroom, left to itself, will naturally trend toward disorder. The messy bedroom won't spontaneously organize itself. This isn't because the universe has some preference for chaos. It's simply a matter of probability. There are so many more ways for things to be disorganized than organized that disorder is overwhelmingly more likely to occur naturally. This entropic arrow is what gives time its direction in our experience. You can't unbreak a dropped glass, can't unburn a piece of paper, can't unmix cream once it's been stirred into coffee. These processes all involve entropy increasing, microstates multiplying, possibility spaces expanding. The arrow of time points in the direction of increasing entropy, from lower probability states toward higher probability ones, from order toward equilibrium. But here's something beautiful and slightly puzzling to contemplate as you rest here. The fundamental laws of physics, at their deepest level, don't actually prefer one direction of time over another. If you could watch a video of particles interacting at the quantum level and then watch the same video played backwards, both would look equally consistent with the laws of physics. The equations that govern how particles move and interact are time-symmetric, meaning they work equally well whether time flows forward or backward. So why do we experience time as flowing in only one direction? The answer lies not in the fundamental laws themselves, but in the initial conditions of our universe. The Big Bang started our cosmos in an extraordinarily low entropy state, a condition of remarkable organization and order from which the universe has been gradually unwinding ever since, like a wound spring slowly releasing its tension. This initial low-entropy state is what sets time's arrow pointing toward the future we experience, toward increasing entropy, toward the eventual heat death of the universe billions upon billions of years from now. But don't let that distant end worry you. Here, now, in this present moment, you exist in a universe where time's arrow creates the possibility for all the rich complexity we observe. Stars that burn steadily for billions of years, planets that maintain stable climates, life that grows and evolves and creates meaning and beauty. The arrow of time isn't something to fear. It's what makes experience possible, what allows cause to precede effect, what gives structure and significance to the unfolding story of existence. As you breathe slowly and deeply, consider how each breath itself demonstrates time's arrow. You inhale oxygen and exhale carbon dioxide. Your body extracts energy from food through processes that increase the universe's total entropy slightly. Your neurons fire in sequences that create thoughts, memories, experiences, all of these processes flowing forward in time, all of them consistent with the gentle but inexorable arrow that points from past to future. You are, in a very real sense, a beautiful temporary eddy of low entropy in a universe gradually trending toward equilibrium, a brief but meaningful structure of order and awareness in the cosmic flow. And yet, even this simple picture of time as a dimension with a direction is just the beginning of time's mysteries. When we look more closely at how time actually behaves, especially when matter moves very fast or gravity becomes very strong, we discover that time is even stranger than Minkowski's four-dimensional spacetime might suggest. Time, it turns out, is not the rigid, absolute, universal metronome that our intuitions tell us it should be. Time is flexible, malleable, relative, different for different observers depending on their motion and location in gravitational fields. Understanding this relativity of time is where our journey takes us next. Einstein's revolution, relativity, and time. Picture yourself standing perfectly still on a train platform on a warm summer evening. The air is calm, the station quiet. In the distance, a train approaches, growing larger as it speeds toward where you stand. As it passes, you see inside one of the windows a person sitting peacefully, reading a book, appearing motionless from their own perspective even as they hurtle past you at high speed. From your point of view on the platform, they're moving rapidly. From their point of view inside the train, they're perfectly still, and it's you and the platform that are moving backward. Neither perspective is more correct than the other. Motion, as Galileo understood centuries ago, is relative. But Einstein realized something profound that goes far beyond this simple relativity of motion. He understood that if the speed of light is constant for all observers, something we know to be true from careful measurements, then time itself must be relative too. This insight, developed in his special theory of relativity in 1905, revolutionized our understanding of time and space in ways that still feel almost magical more than a century later. Here's the heart of special relativity's strange but experimentally verified truth. Time passes at different rates for observers moving at different speeds. If you could watch a clock on that speeding train as it rushed past the platform, and if the train were moving at a significant fraction of the speed of light, you would see that clock running slower than an identical clock you hold in your hand on the platform. This isn't an illusion or a trick of perception. From the perspective of physics, from the perspective of reality itself, less time genuinely passes for objects in motion relative to objects at rest. This phenomenon is called time dilation, and while it sounds like science fiction, it's an established fact that we rely on every single day. Consider the global positioning system, the network of satellites orbiting Earth that tells your phone exactly where you are. These satellites orbit at an altitude of about 20,200 kilometers above Earth's surface, traveling at speeds of approximately 14,000 kilometers per hour. According to special relativity, the clocks on these satellites should run slower than clocks on Earth's surface because they're moving so fast. Specifically, they should lose about 7 microseconds per day compared to ground clocks. But that's not the whole story. Einstein's general theory of relativity, published in 1915, adds another layer to this temporal complexity. General relativity reveals that gravity itself affects time, that massive objects like Earth curve spacetime around them, and that this curvature causes time to pass differently at different distances from the gravitational source. The GPS satellites, being much farther from Earth's center than we are on the surface, experience weaker gravity. According to general relativity, clocks in weaker gravitational fields tick faster than clocks in stronger gravitational fields. The satellite clocks should gain about 45 microseconds per day compared to clocks on Earth. When you combine both effects, the moving satellites lose 7 microseconds but gain 45 microseconds, for a net gain of 38 microseconds per day. This might not sound like much, but remember that GPS works by measuring precisely how long it takes radio signals to travel from satellites to your receiver. Those signals travel at the speed of light, about 300,000 kilometers per second. In 38 microseconds, light travels about 11 kilometers. If GPS didn't account for these relativistic time dilation effects, your phone's location would be off by more than 10 kilometers after just one day. Within a week, the errors would accumulate to make GPS completely useless for navigation. Think about what this means practically. Every time you use your phone to navigate, every time you request directions or check your location on a map app, the software is quietly accounting for Einstein's relativity. The system is compensating for the fact that time passes differently for satellites in orbit than for you on Earth's surface. Without this compensation, without corrections based on both special and general relativity, GPS simply wouldn't work. The satellites would report times that were out of sync with ground stations, and the triangulation calculations that determine your position would yield nonsensical results. The engineers who designed GPS understood this from the beginning. Before the first satellites were launched, physicists calculated exactly how much the orbital atomic clocks would gain compared to ground clocks. They deliberately set the satellite clocks to tick at a rate of 10.22999999543 MHz instead of the standard 10.23 MHz, making them run slightly slower on the ground. Then, when the satellites reached orbit and began experiencing the relativistic effects of their high speed and higher altitude, the deliberately slow clock sped up to exactly the right rate, ticking in perfect synchronization with ground clocks despite being in a completely different gravitational and kinematic environment. This isn't just a one-time correction either. The GPS system continuously monitors the satellite clocks, comparing them with ground-based atomic clocks, making tiny adjustments to account for variations in satellite orbits and other effects. The whole system is a practical demonstration that Einstein was right about time's malleability, that time genuinely does pass at different rates in different circumstances. The fact that GPS works perfectly, that it can pinpoint your location to within meters, is powerful evidence that Einstein was right about time's relativity. Time genuinely does pass at different rates depending on how fast you're moving and how deep you are in a gravitational field. This isn't philosophy or speculation. It's engineering reality, built into the satellite's atomic clocks, which are deliberately set to tick at a slightly different rate on the ground before launch, so they'll keep perfect time once in orbit. But GPS satellites aren't the only place we've confirmed time dilation. Particle accelerators provide another testing ground. When physicists accelerate particles to speeds approaching that of light, something remarkable happens. Many subatomic particles are unstable, decaying after characteristic lifetimes measured in fractions of a second when they're at rest. But when these same particles are accelerated to high speeds, they live longer as measured by laboratory clocks, sometimes many times longer than their rest lifetimes would predict. The particles aren't fundamentally different. They haven't been made more stable by acceleration. What's changed is time itself. From the particle's perspective, moving in its own reference frame, it lives exactly as long as it would at rest. But from the laboratory's perspective, watching the fast-moving particle, time is passing more slowly for the particle. Its internal clock, the quantum processes that govern its decay, are running in slow motion. So the particle travels farther, lasts longer in laboratory time, exactly as special relativity predicts. One particularly striking example involves particles called muons, created when cosmic rays strike Earth's upper atmosphere. Muons decay with a half-life of about 2.2 microseconds when at rest. At the speed these cosmic ray muons travel, about 98% of light speed, they should decay long before reaching Earth's surface, even if they started at the very top of the atmosphere. Simple calculations show that in 2.2 microseconds, even at 98% light speed, a muon travels only about 660 meters. But the atmosphere extends many kilometers above Earth's surface. And yet, muons do reach the surface in abundance. We detect them constantly in laboratories at sea level. How is this possible? Time dilation provides the answer. From Earth's perspective, the muons' clocks run slowly due to their high speed. Their 2.2 microsecond half-life stretches to about 10 times longer in our reference frame, giving them enough time to traverse the atmosphere. From the muons' perspective, something different but equivalent happens. The atmosphere appears contracted along the direction of motion due to length contraction, another consequence of special relativity, so the distance to Earth's surface is much shorter than it appears to us. These experimental confirmations of time dilation aren't rare or controversial. They're routine, observed countless times in different contexts. Atomic clocks flown around the world on airplanes show the predicted relativistic time differences when compared to clocks left on the ground, matching relativity's predictions to exquisite precision. Particle lifetimes in accelerators behave exactly as special relativity predicts. Gravitational redshift, the frequency change of light climbing out of gravitational fields, has been measured in numerous experiments, from light climbing from the sun's surface to photons rising just a few meters in Earth's gravity. This accumulated evidence makes time dilation one of the most thoroughly verified predictions in all of physics. It's not speculative or theoretical in the sense of being uncertain. It's established fact, as solid as any scientific knowledge can be. Time genuinely is relative, genuinely does pass at different rates for different observers, genuinely is woven together with space into the four-dimensional fabric of space-time. Let this settle into your awareness as you rest here. Time is not a universal constant. There is no cosmic clock ticking away the same seconds for everyone everywhere. Instead, every object in the universe has its own proper time, its own personal experience of duration that depends on its motion through space and its location in gravitational fields. The time you experience right now, lying here peacefully, is genuinely your time, slightly different from the time experienced by someone moving past you quickly or someone standing on a mountaintop where gravity is slightly weaker. This relativity of time leads to one of physics' most famous thought experiments, the twin paradox. Imagine two twins, one who stays home on Earth and one who embarks on a journey to a distant star in a spacecraft traveling at nearly the speed of light. Years pass for the Earth-bound twin, decades perhaps. But for the traveling twin experiencing significant time dilation, far less time passes. When the traveling twin returns home, they find themselves younger than their sibling who stayed behind. This isn't science fiction. It's a real consequence of special relativity, confirmed by experiments with particles and atomic clocks. At speeds we encounter in everyday life, these relativistic effects are tiny, completely negligible. A person driving in a car all day ages perhaps a few nanoseconds less than someone sitting still, a difference far too small to measure or matter practically. But the effects are there, real, woven into the fundamental structure of spacetime itself. And at speeds approaching light speed, or in strong gravitational fields like those near black holes, time dilation becomes dramatic and impossible to ignore. Near the event horizon of a black hole, where gravity becomes phenomenally intense, time dilation reaches extremes that boggle the mind. If you could somehow hover safely just above a black hole's event horizon and watch a friend far away in normal space, you would see them moving extremely quickly, living their entire life perhaps in what seems like moments to you. Meanwhile, from their distant perspective, you would appear nearly frozen in time, your movements glacially slow, each second of your experience stretched into hours or days of theirs. You would each be experiencing time at profoundly different rates, both perspectives equally valid, neither more real than the other. General relativity also predicts, and experiments have confirmed, that light itself is affected by gravity through what's called gravitational redshift. As light climbs out of a strong gravitational field, it loses energy, its wavelength stretches, its color shifts toward the red end of the spectrum. This is time dilation at work on light, photons being affected by the curvature of spacetime just as clocks are, just as you are. Think about what all this means for the nature of time. Time isn't some separate entity independent of space and matter. Time is part of spacetime, curved and shaped by mass and energy. Where there's more mass, spacetime curves more sharply, and time passes more slowly. Time is a dimension, yes, but it's a dimension intimately connected to the others, responding to the distribution of matter and energy throughout the cosmos. And here's perhaps the most peaceful implication of all this relativity. There is no absolute simultaneity in the universe. Events that appear simultaneous to one observer may appear to occur in sequence to another observer moving differently or located differently in a gravitational field. The relativity of simultaneity means there's no universal now that extends throughout the entire cosmos. Instead, each observer has their own present moment, their own slice through space-time that they experience as now. This doesn't mean time is an illusion or that the past and future don't exist in any meaningful sense. It means instead that time is richer and more complex than our everyday intuitions suggest. It means the universe is a four-dimensional whole, a space-time manifold where different observers carve out different but equally valid three-dimensional spaces at different moments of their proper time. As you breathe slowly here, relax into this understanding. Your now, your present moment, is real and significant, but it's also personal, tied to your specific world line through space-time, your particular path through this four-dimensional reality. Someone moving very fast relative to you has a different now, a different present moment that might include events in what you consider your future or past. And yet somehow, despite these different perspectives, the universe maintains its consistency, its coherence. The space-time interval between any two events, a mathematical quantity combining spatial and temporal separations, remains the same for all observers, regardless of their motion or location. This invariance of the space-time interval is what allows physics to work, what ensures that different observers can translate between their different perspectives and agree on the fundamental structure of reality. Einstein's relativity reveals time as dynamic rather than static, relative rather than absolute, intertwined with space rather than separate from it. This vision of time is simultaneously strange and beautiful, challenging our intuitions while offering new ways to understand our place in the cosmos. And as we'll explore next, when we venture into the quantum realm where the very small governs, time becomes even more mysterious, presenting puzzles that physicists still grapple with today. Time at the quantum level. If relativity seems strange, wait until you encounter what happens to time when we descend to the quantum scale, to the realm of atoms and subatomic particles, where the rules governing reality shift in ways that seem almost impossible from our everyday perspective. Here, in the quantum world, time presents puzzles so profound that physicists have been wrestling with them for decades. Puzzles with names like the problem of time, that hint at just how fundamentally mysterious temporal flow becomes when you try to marry quantum mechanics with general relativity. Let's start with something gentle, something to ease us into quantum strangeness. In ordinary quantum mechanics, the kind developed in the early 20th century to explain atoms and molecules, time still plays its familiar role. The Schrödinger equation, which describes how quantum systems evolve, treats time as a parameter, a background against which quantum wave functions change and develop. In this framework, time ticks along just as you might expect, providing a stage on which the quantum drama unfolds. But even here, time has some peculiarities. In quantum mechanics, certain pairs of properties are connected by Heisenberg's uncertainty principle. You can't know both a particle's position and momentum with perfect precision simultaneously. The more precisely you measure one, the less precisely you can know the other. There's a similar relationship involving time and energy. If you want to measure the energy of a quantum system very precisely, you must observe it for a longer time. If you want to determine exactly when something happens at the quantum level, you sacrifice precision in determining its energy. Time and energy are linked by an uncertainty relation just as position and momentum are. This time-energy uncertainty might seem abstract, but it has real consequences. It means that quantum systems can borrow energy from the vacuum for brief moments, creating virtual particles that pop into existence and vanish again faster than you could possibly detect them directly, as long as they do so within the time limit set by the uncertainty principle. These quantum fluctuations are real, measurable through their subtle effects on atoms and light. They're part of the constant quantum buzz underlying all of reality, a seething foam of possibility that exists even in supposedly empty space. But the real temporal puzzles emerge when we try to apply quantum mechanics to gravity itself, when we attempt to create a quantum theory of spacetime. Remember that in general relativity, time is part of the dynamic structure of spacetime, curved and shaped by matter and energy. But in quantum mechanics, we typically assume a background spacetime, a fixed stage on which quantum events occur. These two frameworks seem fundamentally incompatible in how they treat time. This incompatibility comes to a head in the Wheeler-DeWitt equation, an attempt formulated in the 1960s to describe the quantum state of the entire universe. When John Wheeler and Bryce DeWitt tried to combine quantum mechanics with general relativity through this equation, something strange happened. Time disappeared from the mathematics entirely. The Wheeler-DeWitt equation describes a quantum wave function for the universe, but this wave function doesn't evolve in time. It simply is. Time, at the most fundamental level of this quantum description of gravity, seems to vanish. This is the so-called problem of time in quantum gravity. How can time emerge from a theory where the fundamental equation contains no time variable? How can the universe evolve if its quantum state is static? Physicists have proposed various solutions to this puzzle, and exploring them reveals deep insights about time's nature. One approach involves what's called the Page-Wouters mechanism, proposed by Don Page and William Wouters in 1983. Their idea is beautiful in its simplicity. Perhaps time emerges from quantum entanglement. Imagine the universe as containing something we can think of as a clock, some quantum system that changes in measurable ways, and then everything else which we can call the rest of the universe. These two parts can become quantum entangled, their states linked in the peculiar way quantum systems can be connected across space. Now, when you, as an observer who's part of the rest of the universe section, measure the clock quantum mechanics as you force it into a particular state, a specific time reading. But because the clock is entangled with everything else, measuring the clock's time also forces the rest of the universe into a corresponding state, the state it should be in at that particular time. From your perspective inside the universe, you experience time flowing as you make successive measurements of this quantum clock, even though from a perspective outside the universe, if such a thing were possible, the overall quantum state might appear timeless. This is subtle and perhaps difficult to grasp fully, especially in a state of deep relaxation, but the essential idea is this: time might not be fundamental. Instead, time might emerge from something more basic, from the quantum entanglement structure of the universe, from relationships between different parts of the cosmos. Time would then be a bit like temperature, which seems like a fundamental property when you feel hot or cold but actually emerges from the microscopic motions of countless atoms. No individual atom has a temperature, only collections of many atoms in relation to each other have this property. Similarly, perhaps no individual piece of the universe has time, but the relationships between pieces, their quantum entanglements, give rise to the experience of temporal flow. Another approach to the problem of time involves identifying some quantity within the universe that can serve as a clock, some variable that changes monotonically, always in the same direction, which we can use to parameterize the universe's evolution even though the Wheeler-DeWitt equation itself is timeless. This is sometimes called WKB time, named after a mathematical approximation method. In this view, time emerges approximately in certain regimes, particularly when the universe is large and classical, even though time isn't present at the most fundamental level of the quantum description. What's deeply peaceful about all these quantum puzzles around time is that they reveal how much we still have to discover, how many mysteries remain even in our most advanced physical theories. The universe is not fully explained, not completely understood, and that's wonderful. It means reality has depths we've barely begun to plumb, layers of meaning and structure waiting to be uncovered. It means the journey of understanding is far from over, that future generations will see further than we can today, perhaps solving the problem of time in ways we can't yet imagine. And yet, despite these deep quantum mysteries, despite time possibly being emergent rather than fundamental, your experience of time remains real and meaningful. The succession of moments you live through, the memories you form, the future you anticipate, all of these are genuine features of your existence in this universe. Whether time is fundamental or emergent, it's undeniably part of your reality, woven into the structure of your consciousness and experience. As you rest here, breathing slowly, consider this: you're a quantum system yourself, made of countless particles whose behaviors are ultimately governed by quantum mechanics. Your neurons fire according to quantum principles, electrochemical signals cascading through quantum processes in your brain. Your thoughts, your awareness, your experience of time passing, all of these might ultimately be quantum phenomena, however emergent and classical they appear at the macroscopic scale of your everyday consciousness. The quantum realm is strange, yes, but it's also intimately yours. You're made of quantum fields and particles, excitations in the fundamental fields that permeate all of space. Your body, the atoms that compose you, existed in other forms before you were born and will exist in other configurations after you die. But right now, in this moment, they're arranged in a pattern that is you, that experiences time, that creates and holds memories, that exists as a conscious observer of the quantum universe. This temporary arrangement, this pattern you call yourself, is precious precisely because it's temporary, because it exists in time, because it changes and grows and eventually will dissolve back into the larger patterns of the cosmos. Time's presence, whether fundamental or emergent, is what makes your existence possible, what distinguishes the pattern that is you from static information. You're not just a structure in space. You're a structure in space-time, a four-dimensional process, an ongoing event in the universe's unfolding story. And that story, that cosmic narrative, brings us to another way of thinking about time entirely, a perspective that sees past, present, and future not as separate regimes but as equally real, all existing together in what physicists and philosophers call the block universe. Understanding this view of time might be the most peaceful revelation of all. The block universe and eternalism. Imagine that you could step outside of time entirely, that you could view the entire history of the universe from beginning to end all at once, spread out before you like a vast landscape. In this view, the Big Bang wouldn't be something that happened long ago. It would be right there, visible, just as present as this current moment and as the far distant future. Every event that has ever occurred or will ever occur would exist simultaneously, frozen, eternal, like scenes in a completed film or pages in a finished book. This is the block universe view, also called eternalism in philosophical discussions, and it's a natural consequence of taking Einstein's relativity seriously. If time is a dimension similar to space, if past and future are as real as different locations in space, then why should we privilege the present moment over any other? Why should now be special when here isn't special in space? The block universe sees all of space-time as a single four-dimensional object. Your entire life, from your birth to your death, forms a continuous structure in this block, a world line threading through space-time. Every moment you've experienced and will experience exists somewhere in this four-dimensional structure. The you reading these words is one cross-section of your world line, one slice through your four-dimensional self. The you who was born is another slice years earlier along the world line. The you who will someday face your last moment is another slice years later along that same continuous thread. In the block universe, nothing moves, nothing flows, nothing becomes. Everything simply is. The appearance of flow, the subjective experience you have of time passing and events becoming, emerges from your perspective as a conscious being embedded within the block, a being whose thoughts and memories are themselves structures within space-time, not something separate from it. This might sound coldly deterministic, and indeed, the block universe view does suggest a kind of four-dimensional determinism where the entire history of the universe exists as a completed whole. But there's something deeply peaceful about this perspective too, something that can bring comfort if you let it settle into your understanding. In the block universe, nothing is ever truly lost. Every good moment you've experienced still exists in space-time, just as real now as when you first lived it, just located at a different temporal coordinate. Every person you've loved who has died still exists at their temporal location in the block, living their life eternally in their section of space-time. Your past isn't gone, merely behind you on your world line. As real as a place you visited on a map is still real even though you're no longer there. Similarly, your future already exists in this view, spread out ahead of you on your world line, as real as your past, even though you haven't experienced it yet. This might seem to eliminate free will, to suggest that you're simply following a predetermined path through space-time. But that's not quite right. Your decisions, your choices, your moments of deliberation, all of these are part of the block, part of the structure of how your world line is shaped. You make real choices even if those choices are, from a four-dimensional perspective, already part of the eternal structure of the block. Think of it like this. When you read a novel, the characters make choices, face dilemmas, decide their fates. The fact that these choices are already written on the pages, that the book's ending exists before you read it, doesn't make the characters' choices any less real within the story. Similarly, from within the block universe, from your embedded perspective as a conscious being whose existence unfolds along a world line, your choices are genuine, your experiences are real, your decisions matter, even if from an impossible external perspective those choices are already part of the four-dimensional structure. The block universe view is supported by the relativity of simultaneity that we explored earlier. Remember that different observers moving at different speeds or located in different gravitational fields have different definitions of now, different ways of slicing the four-dimensional block into three-dimensional spaces at different moments. If simultaneity is relative, if there's no universal present moment, then the idea that only the present exists, only now is real, becomes untenable. Either all moments are equally real, as the block universe suggests, or we'd have to privilege one particular reference frame as special, which would contradict the principle of relativity. But the block universe isn't the only way to think about time structure. Some philosophers and physicists prefer the growing block view, which says that the past and present exist but the future doesn't yet. In this picture, new moments are continually being added to reality as time flows forward. The block grows, its future edge advancing like a wave across space-time. This view tries to preserve the intuition that the future is open, genuinely undetermined, while accepting that the past is fixed and real. The growing block view has its own comforts and challenges. It preserves a sense of genuine temporal becoming, of moments coming into existence, which matches our subjective experience more closely than the static block universe. But it faces difficult questions. What is this edge of the block, this advancing present moment? How does it move and what determines its speed? And doesn't the relativity of simultaneity make it problematic to define a universal growing edge? These questions don't have easy answers, and physicists and philosophers continue to debate them. But for our purposes, resting here peacefully, what matters is not which view is correct, but rather what these different perspectives reveal about time's deep nature. All these views agree that time is real, that it has genuine structure, that it's not an illusion. They differ in how they characterize time's reality, whether they see all moments as equally real or only some moments as currently existing. But none of them suggest that time is merely subjective or that the flow you experience is purely in your mind. Time is part of the universe's objective structure, woven into the fabric of reality itself. There's something liberating about contemplating these different views of time. They remind us that our everyday intuitions about time, while useful and meaningful for navigating daily life, don't exhaust time's possibilities. Reality is richer than our immediate perceptions suggest, structured in ways that transcend our ordinary experience. You exist not just in this present moment, but as an extended four-dimensional entity, a process, an event in the universe's great story, whether that story is complete and eternal like a finished film or growing like a novel being written one word at a time. And you know what's beautiful? Even if the block universe view is correct, even if all of history exists eternally and simultaneously from some impossible outside perspective, from your embedded perspective, time still flows, moments still succeed one another, you still experience the passage from past through present toward future. The block universe, if it exists, includes within its structure the experience of temporal flow, your experience, your consciousness moving along your world line, encountering each moment in sequence, creating memories, forming plans, living a life that feels entirely real and meaningful from the inside, even if it appears frozen and eternal from some imagined outside view. As you breathe here, relaxing deeper, let yourself appreciate the mystery and majesty of this. You're a conscious being aware of time's passage, embedded in a universe whose temporal structure physicists and philosophers still debate. Your experience of time might be one slice through a four-dimensional block, or it might be riding the growing edge of reality as new moments crystallize into existence. Either way, your experience is real, your life meaningful, your moments precious exactly because they're structured in time, because they succeed one another, because they form a narrative, a story, a journey from birth toward whatever comes next. Time's direction and asymmetry. We've talked about the arrow of time before, about how entropy gives time its direction from past toward future. But let's deepen that understanding now, exploring in gentle detail why time has an arrow at all when the fundamental laws of physics are time-symmetric, working equally well forward or backward. Picture a glass of water sitting on a table. Now imagine dropping a single drop of ink into that water. What happens? The ink disperses, spreading through the water, diffusing until eventually the entire glass is tinted a uniform pale color. You've seen this happen countless times in various forms. Food coloring in water, cream in coffee, perfume dispersing through a room. It's such a familiar phenomenon that it seems entirely natural, entirely unremarkable. But now imagine running this process backward. Imagine the uniformly tinted water spontaneously separating, all the ink molecules gathering together, concentrating into a single drop, lifting out of the water. This would be equally consistent with the fundamental laws of physics. Every collision between water molecules and ink molecules in the original dispersal process could, in principle, happen in reverse. The laws governing molecular interactions are time-symmetric. They don't forbid the reverse process, and yet we never see it happen. We never see ink spontaneously unmixing from water. We never see broken glasses reassembling themselves. We never see scrambled eggs unscrambling back into shell and yolk and albumin. Why not? The answer lies in probability and entropy. While the reverse processes aren't forbidden by fundamental laws, they're fantastically improbable. There are vastly more ways for ink to be spread throughout water than concentrated in a drop. The uniform tint corresponds to a high-entropy state, the drop to a low-entropy state. Starting from high entropy, spontaneous fluctuations toward low entropy are possible but extraordinarily unlikely, so unlikely that they've never been observed for macroscopic objects despite all the time humans have been observing nature. This is the thermodynamic arrow of time, emerging not from time asymmetric fundamental laws but from the statistical properties of systems with many particles. It's why eggs scramble but don't unscramble, why living things age and deteriorate, why machines wear out, why stars burn down rather than building up. All these processes involve entropy increasing, possibility spaces expanding, orderly low-entropy states evolving toward disordered high-entropy equilibrium. And this thermodynamic arrow, this tendency for entropy to increase, is intimately connected to our psychological experience of time's direction. You remember the past but not the future. You can affect the future but not the past. Causes precede effects from your perspective, never the reverse. All these psychological and causal arrows point in the same direction as the thermodynamic arrow, from past toward future, from lower entropy toward higher entropy. This isn't coincidence. Memory formation is itself an entropy-increasing process. Creating a record of an event, whether in your brain's neural networks or in any other storage medium, requires putting some physical system into a specific ordered state that correlates with the event being recorded. This decreases the local entropy of the recording medium but increases the total entropy of the universe overall when you account for the heat and disorder generated in the recording process. Memory only works in one temporal direction, the direction of increasing total entropy. Similarly, our ability to affect the future but not the past stems from entropy's arrow. We can arrange things now in ways that influence what happens later because we can manipulate current low-entropy states. But we can't reach back and change high-entropy past states because the information about specific configurations has been lost to entropy increase, scrambled beyond practical recovery. Here's something profound to contemplate as you rest. The reason you experience time flowing from past to future, the reason you age, the reason you remember yesterday but not tomorrow, all of this ultimately traces back to the initial conditions of the Big Bang. The universe started in an extraordinarily low entropy state, and it's been unwinding, entropy increasing ever since. Your life, your consciousness, your experience of time's arrow, all of these are possible only because the universe began in this improbable low-entropy configuration. Why did the universe start with such low entropy? This is one of cosmology's deepest questions, one without a fully satisfactory answer yet. Some physicists suggest it might be related to quantum fluctuations in the very early universe. Others propose it might be a consequence of the particular physics of inflation, a period of extraordinarily rapid expansion hypothesized to have occurred in the universe's first fraction of a second. Still others wonder whether we can even meaningfully ask why the initial conditions were what they were, whether the question assumes a kind of causation that breaks down at the universe's beginning. But whatever the answer, the fact remains. Time's arrow emerges from entropy's increase, and entropy increases because the universe started in a special low-entropy state. This thermodynamic arrow gives structure to your life, creates the possibility for memory and anticipation, for cause and effect, for narrative and meaning. Without entropy's arrow, there would be no becoming, no change from past through present to future, no experience of time passing at all. There are other arrows of time too beyond the thermodynamic one. There's the cosmological arrow, the fact that the universe is expanding rather than contracting, space growing larger with time rather than smaller. There's the electromagnetic arrow, the fact that we see electromagnetic waves radiating outward from sources, spreading their influence into the future, rather than converging waves collapsing onto targets from the future into the past. There's the quantum mechanical arrow associated with wave function collapse, though this one is controversial and depends on your interpretation of quantum mechanics. All these various arrows remarkably point in the same direction. This alignment isn't necessarily guaranteed by fundamental laws, but it appears to be a feature of our actual universe. Some physicists and philosophers speculate about whether these arrows might reverse if the universe ever stopped expanding and began contracting in a big crunch scenario. Would entropy begin decreasing? Would we remember the future and forget the past? These are fascinating questions, but they're probably academic since current observations suggest our universe will expand forever, never contracting, entropy increasing without end toward a final state of maximum entropy called heat death. Heat death sounds ominous, but it's unfathomably far in the future, so distant that the concept almost loses meaning. Long before heat death, perhaps 10 to the power of 100 years from now or more, stars will have burned out, black holes will have evaporated through Hawking radiation, and matter itself will have decayed into radiation. But even contemplating such vast timescales serves a peaceful purpose right now. It reminds you that your moment, this present instant, is part of an incomprehensibly larger story, a cosmic narrative spanning timescales that dwarf human life, that dwarf the entire history of civilization, that dwarf even the lifespan of stars. Your life is brief, yes, but it's real and meaningful. A beautiful eddy of low entropy and organized complexity in the universe's long, slow slide toward equilibrium. You're like a wave on an ocean, a temporary pattern that emerges, exists for a time, then dissolves back into the larger whole. But while you exist, while this pattern persists, you experience, you feel, you think, you love, you create meaning and beauty, all of these made possible by time's arrow, by entropy's direction, by the universe's special initial state. As you breathe here, letting each exhalation carry away a bit more tension, consider that every breath is irreversible, entropy increasing slightly with each cycle. You can't unbreathe, can't extract exhaled carbon dioxide from the air and convert it back into oxygen in your lungs. Your life flows in one direction, from birth toward death, from innocence toward experience, from potential toward actualization. This directionality isn't something to mourn. It's what makes experience possible, what distinguishes your life from a static object. You're a process, an event, a becoming, and all of this requires time's arrow, time perception and the human experience. All this physics of time, all these abstract concepts about relativity and entropy and block universes might seem distant from your immediate subjective experience of time. But your brain's perception of time is itself fascinating, revealing how consciousness creates a sense of temporal flow from the neural processes unfolding in your head right now as you rest here. Time perception isn't mediated by a single sense organ like vision or hearing. There's no time receptor in your body detecting temporal flow the way your eyes detect light. Instead, time perception emerges from complex neural processes distributed throughout your brain, involving multiple regions including the prefrontal cortex, the cerebellum, and the basal ganglia. These areas work together to create your subjective sense of duration, your feeling that time is passing, your ability to estimate intervals and sequence events. One influential model of time perception envisions an internal clock based on a pacemaker accumulator mechanism. In this model, a neural pacemaker generates pulses, perhaps related to neural oscillations or the rhythmic firing of certain neurons. When you need to time something, attention acts like a switch, closing to allow pulses to flow into an accumulator, a kind of neural counter. The more pulses accumulated, the longer the duration you perceive. When the timed interval ends, attention opens the switch, stopping the pulse flow. You judge elapsed time based on how many pulses accumulated. This model explains several quirks of time perception. When you're paying close attention to time itself, watching a pot boil or waiting for a bus, time seems to drag because your full attention is focused on accumulating pulses. When you're absorbed in an engaging activity, experiencing what psychologists call flow state, you're not attending to time passage. The attention switch is open, pulses aren't accumulating, and you lose track of time entirely, surprised when you finally look at a clock to discover hours have passed. Consider how this plays out in different situations. When you're bored, sitting through a tedious meeting or waiting in a slow-moving line, your attention often turns toward monitoring time itself. You check your watch frequently, notice every minute that passes, wonder when the ordeal will end. This heightened attention to temporal passage makes the internal clock accumulate more pulses, stretching your subjective experience of duration. 5 minutes feels like 15. An hour feels like 3. Contrast this with moments of deep engagement, times when you're completely absorbed in a task that perfectly matches your skill level with appropriate challenge. Perhaps you're creating art, lost in the flow of brush on canvas, every stroke emerging naturally without forced deliberation. Perhaps you're playing music, your fingers finding notes intuitively, the melody flowing through you rather than being constructed by conscious effort. Perhaps you're writing, words appearing on the page in rapid succession as ideas crystallize into language faster than you can type. Perhaps you're solving a complex problem, each insight building on the last, the solution revealing itself through sustained concentration. In these moments of flow, self-consciousness vanishes. You're not thinking about yourself thinking. You're not monitoring your performance or worrying about the outcome. You're simply doing, fully present in the activity, attention completely absorbed by the task at hand. And time disappears from awareness. You're not attending to its passage, so your internal clock's accumulator remains empty. When you finally emerge from flow, whether because the task completes or you're interrupted, you're often shocked by how much time has passed. What felt like 20 minutes was actually 2 hours. What seemed like an hour was only 10 minutes. Your subjective duration and objective clock time have completely diverged. Flow states are particularly fascinating from a neurological perspective. When you're in flow, deeply engaged in something that perfectly matches your skill level with appropriate challenge, several things happen in your brain. The default mode network, active during mind-wandering and self-referential thought, quiets down. The prefrontal cortex, involved in self-consciousness and executive control, shows reduced activation. Meanwhile, areas associated with focused attention and task performance remain highly active. This pattern creates the subjective experience characteristic of flow: loss of self-consciousness, time distortion, effortless concentration, the activity feeling automatic yet controllable. Brain imaging studies have revealed fascinating details about flow's neural correlates. When people engage in flow-inducing activities while inside brain scanners, researchers observe increased theta wave activity in the frontal regions of the brain, combined with moderate alpha wave activity in frontal and central areas. Theta waves, oscillating at about 4 to 8 cycles per second, are typically associated with deep relaxation, meditation, and creative states. Alpha waves, at 8 to 13 cycles per second, appear during calm wakefulness and focused attention. This combination of theta and alpha activity creates an optimal brain state for sustained concentration without mental strain. The neurotransmitter systems involved in flow are equally intriguing. Dopamine, the brain's principal reward and motivation chemical, plays a crucial role. Flow states typically involve increased dopamine release, creating feelings of pleasure and reinforcing the behavior that generated the flow. This is why flow can be addictive in the healthiest sense of the word, why artists lose track of time in their studios, why programmers code through the night, why athletes push through exhaustion to maintain perfect form. The dopamine reward makes the activity intrinsically satisfying, creating motivation that comes from within rather than from external rewards or pressures. Norepinephrine, another key neurotransmitter, also increases during flow. Norepinephrine enhances focus and arousal, helping maintain the intense concentration characteristic of flow states. The locus coeruleus, a small nucleus in the brainstem that produces most of the brain's norepinephrine, appears to be particularly active during flow, maintaining optimal arousal levels that are neither too low, which would lead to boredom, nor too high, which would create anxiety. The experience of time distortion in flow isn't uniform, interestingly. Some research suggests that the direction of time distortion depends on the specific nature of the flow activity. In some forms of flow, particularly those involving physical movement like sports or dance, time often seems to slow down. Athletes report that during peak performance, everything seems to happen in slow motion, giving them more time to react and respond. A basketball player might see the ball's trajectory with crystal clarity, able to adjust their shot mid-flight. A race car driver might perceive individual details of their surroundings with extraordinary precision, making split-second decisions that feel unhurried. This subjective slowing might relate to increased information processing in the brain during high-performance states. When your brain operates at peak efficiency, processing more information per unit time, each moment becomes richer with detail, potentially creating the impression of temporal expansion. It's similar to how frightening situations often seem to unfold in slow motion in memory, possibly because fear triggers heightened attention and information processing, creating denser memories that seem to have required more time to experience. In other forms of flow, particularly those involving sustained creative work or problem-solving, time typically seems to accelerate, hours vanishing in what feels like minutes. This acceleration might relate more directly to the lack of attention to time passage, the complete absorption in the task that prevents the internal clock from accumulating pulses. When you're not monitoring time, When you're not metacognitively aware of your experience as it unfolds, temporal awareness simply vanishes and subjective duration collapses. The relationship between attention and time perception extends beyond flow states. Research has shown that difficult cognitive tasks generally make time seem to pass more quickly than easy tasks, perhaps because difficult tasks demand more attention, leaving less cognitive capacity available for time monitoring. Conversely, when you're understimulated, bored, with plenty of attention available but nothing engaging to direct it toward, that free attention often turns to time monitoring, making minutes drag. The neurotransmitter dopamine plays a crucial role in time perception and flow states. Dopamine is involved in attention, motivation, and reward processing. Drugs that increase dopamine levels, like stimulants, tend to speed up the internal clock, making time seem to pass more slowly than it actually is. Conversely, conditions that reduce dopamine, like some forms of depression or Parkinson's disease, can slow the internal clock, making time seem to race by. Emotion also dramatically affects time perception. Frightening situations trigger the amygdala, part of your brain's threat detection system, which may speed up the internal clock, making scary events seem to last longer than they actually do in retrospect. This time dilation during fear might be adaptive, an evolved response that packs more perceptual information into memory during dangerous situations, helping you learn to avoid similar threats in the future. Your age affects time perception too. As you grow older, time often seems to pass more quickly. A year to a child of 10 represents 1/10 of their entire life, a substantial fraction. A year to someone of 60 represents only 1/60th of their life, a much smaller fraction. Additionally, as you age, you accumulate more routine experiences, more familiar situations. Novel experiences, being processed more deeply by your brain, seem to last longer in memory than routine ones. Childhood, full of novel first experiences, seems in retrospect to have lasted longer than adult years filled with familiar routines. But memory's relationship with time is complex and not always reliable. When you remember an event, you don't retrieve a perfect recording. You reconstruct the memory from fragments, potentially altering it in the process. Your sense of when something happened often comes from inferring temporal order from other information, from contextual clues about what else was happening at the time, not from any intrinsic temporal tag attached to the memory itself. This reconstructive nature of memory means your remembered past isn't quite the same as the past you actually experienced. It's been edited, compressed, reorganized by your brain's memory systems. Events that seemed important get remembered more clearly than trivial moments, even if those trivial moments occupied more actual time. Your life story, as you remember it, is a highly edited version of the raw footage of your experience. And yet, despite all these quirks and distortions, your subjective time perception is real and meaningful. When you experience time slowing during a frightening moment, that experience is genuine even if clocks show the moment was brief. When hours vanish during flow, your loss of time awareness is authentic even if the hours objectively passed. Your internal time, your subjective duration, is as real to you as external clock time, perhaps more so since it's what you directly experience. As you lie here, breathing slowly, notice your time perception in this moment. Are you aware of time passing? Or has your attention drifted away from temporal tracking? Does time seem fast or slow right now? There's no right answer, only your present experience, whatever it may be. Maybe time has seemed to slow as you've relaxed into this peaceful state. Maybe it's felt like just moments since we began, even though quite some time has passed. Both experiences are valid. Both are your brain's time perception system creating subjective duration from neural processes. Your consciousness exists in time, unfolding moment by moment, thought following thought, experience succeeding experience. Even if physicists are right that the block universe exists, that your entire life is laid out four-dimensionally in space-time, your subjective experience is of flowing through that structure, encountering each moment sequentially, building memories of the past, anticipating possibilities in the future, always centered in what you experience as now. This flowing, subjective present moment is where you live, where you experience consciousness, where meaning emerges from the pattern of neural activity in your brain. And while neuroscience can explain much about how your brain creates time perception, the fact of subjective experience itself, the what-it-is-likeness of experiencing time's passage, remains mysterious. How does the brain's processing of information give rise to the feeling of being you, existing now, experiencing this moment? This is the hard problem of consciousness, and it's deeply entwined with the nature of time. But for now, resting peacefully, you don't need to solve that mystery. You can simply appreciate it, marvel at it, the wonder that you exist, aware, conscious, experiencing time's passage, right here, right now, embedded in this universe that's revealed so many of its temporal secrets while still holding more mysteries than any single lifetime could hope to unravel. Cosmic time and the universe's clock. Let's step back now from the intimate scale of your personal time perception and contemplate time on the grandest scales possible: cosmic time, the age of the universe itself, and the question of whether time had a beginning and might someday have an end. Our current best scientific evidence suggests the universe is approximately 13.8 billion years old. This number comes from multiple independent lines of evidence that all converge on the same answer, giving us confidence it's approximately correct. The most direct evidence comes from observations of the cosmic microwave background, a faint glow of radiation filling all of space, the oldest light in the universe, released when the cosmos was just 380,000 years old. Before that moment, the universe was too hot and dense for light to travel freely. Matter existed as a plasma, a soup of charged particles where photons couldn't travel far before being absorbed and re-emitted. But as the universe expanded and cooled, it reached a temperature where electrons could combine with atomic nuclei to form neutral atoms, a process called recombination. Suddenly, light could travel freely through space, streaming outward in all directions. That ancient light, stretched by the universe's expansion from visible wavelengths to microwaves, is what we observe today as the cosmic microwave background. By measuring the detailed properties of this background radiation, its temperature, its tiny fluctuations in different directions, cosmologists can determine how long ago it was emitted and infer the universe's age with remarkable precision. The agreement between this method and others, like observations of distant supernovae and measurements of the universe's expansion rate, gives us confidence in the 13.8 billion year figure. But what does it mean for the universe to have an age? What was there before the Big Bang? Is before even a meaningful concept if time itself began with the Big Bang? These questions take us to the boundaries of physics, where current theories become speculative and uncertain. In general relativity, space-time can have boundaries, edges where it simply begins or ends. The Big Bang might represent such a boundary in the past direction, a moment before which there was no time, no space, no before. Asking what happened before the Big Bang might be like asking what's north of the North Pole, a question that seems grammatical but actually references a non-existent location. Some cosmologists, however, propose that time might extend before the Big Bang. Various theories suggest our observable universe might be part of a larger multiverse where different regions have different properties, or that the Big Bang might represent a bounce, a transition from a previous contracting phase to our current expanding phase, or that quantum mechanics applied to the universe's birth might allow for a kind of quantum tunneling from nothing into existence, though even this nothing is a complex quantum state rather than absolute non-existence. These ideas are fascinating but highly speculative, difficult or impossible to test with current technology. What we can say with confidence is that our observable universe, the region we can see from Earth, is about 13.8 billion years old, having expanded from an extremely hot, dense state to its current cooler, more diffuse configuration. The expansion of the universe itself provides a kind of cosmic clock, a way to measure time on the largest scales. As space expands, distant galaxies recede from us, their light stretched to longer, redder wavelengths by the expansion. By measuring how much a galaxy's light has been redshifted, we can determine how far away it is and how long ago the light we're seeing was emitted. Distant galaxies show us the universe as it was billions of years ago, younger, smaller, denser, hotter. Looking out into space is literally looking back in time. When you see a galaxy a billion light-years away, you're seeing it as it was a billion years ago, because the light has taken a billion years to reach us. The most distant objects we can observe show us the universe when it was less than a billion years old, infant galaxies forming in a cosmos quite different from today's. This cosmic clock, the expansion of the universe, is measurable and consistent, providing a universal time coordinate for cosmology. While relativity tells us there's no universal simultaneity for observers in relative motion, there is a natural time coordinate for the universe as a whole, defined by the expansion itself. Observers at rest with respect to the cosmic microwave background, not moving relative to the average motion of matter in the universe, share this cosmic time. It's the time measured by someone surfing along with the universe's expansion, the time that appears in cosmological equations describing how the universe evolves. And evolve it does. The universe's large-scale structure has changed dramatically over cosmic time. In the beginning, matter was distributed almost uniformly, with only tiny density variations. But those variations, imprinted during an early period of rapid expansion called inflation, grew over time through gravity's inexorable pull. Denser regions attracted more matter, becoming denser still, eventually collapsing into the first stars, galaxies, and galaxy clusters. Structure formed hierarchically, small objects first, larger structures later, a cosmic web of galaxies strung along filaments surrounding vast cosmic voids. This evolution of cosmic structure provides another clock, another way to date the universe. By observing how clustered galaxies are, how structure has developed, cosmologists can infer the age required for gravity to have organized matter into the patterns we see. Again, this method agrees with others, all pointing to an age around 13.8 billion years. But what about time's future? Will the universe expand forever, or might it someday recollapse? Current observations suggest eternal expansion. The universe's expansion is actually accelerating, driven by something we call dark energy, a mysterious component that makes up about 68% of the universe's total energy, but whose nature remains unknown. If this acceleration continues, the universe will expand forever, growing ever larger, ever colder, ever more diffuse. In this scenario, cosmic time stretches infinitely into the future. Stars will eventually exhaust their fuel, galaxies will grow dark, black holes will evaporate through Hawking radiation over timescales of 10 to the power of 100 years or more, and eventually, after incomprehensible eons, the universe will approach a state of maximum entropy, heat death, where no free energy remains to do useful work, where temperature is uniform throughout, where nothing interesting can happen anymore. This fate sounds depressing, but remember how unfathomably distant it is. By the time heat death approaches, the current epoch, the age of stars and galaxies and life, will be an infinitesimally brief flash in the universe's long history, less than a nanosecond compared to a human lifespan. And you, right now, exist in that brief flash, in the cosmos's youth when stars still shine, when complex structures persist, when consciousness is possible. Your moment in cosmic time is precious exactly because it's fleeting on cosmic scales. The universe won't always be hospitable to life, won't always contain conditions suitable for complexity and consciousness. But now it does, and you're here, aware, experiencing this special epoch when the universe is old enough to have formed stars and planets but young enough that those stars still burn, providing the energy that makes life possible. As you breathe slowly here, consider your place in cosmic time. The atoms in your body were forged in ancient stars that lived and died before our sun was born. The oxygen you're breathing, the carbon in your cells, the iron in your blood, all of these were created through nuclear fusion in stellar cores or in supernova explosions billions of years ago. You're made of stardust, quite literally, your substance recycled from previous generations of stars. And you exist at a particular moment in cosmic history, about 8 billion years after the beginning, in a universe that's had time to develop the complexity necessary for life but hasn't yet evolved to the point where such complexity is impossible. This moment, your moment, is special not because you're at the center of anything, but because you're at a special time, an age when the cosmos can support conscious observers, when structure and organization persist against entropy's gradual increase. Your personal time is nested within cosmic time, your heartbeat a rapid flutter compared to the stately rhythms of stellar evolution and galactic rotation, and yet both are real, both are part of time's grand structure spanning scales from the Planck time of 10 to the power of -43 seconds, the smallest meaningful time interval in quantum physics, to the vast eons of cosmic evolution stretching into the deep future. Time travel, physics, and possibilities. We've explored time from many angles, from relativity's flexible temporal flow to quantum mysteries to the universe's cosmic clock. But we haven't yet addressed one of the most intriguing questions about time, the question that dominates science fiction and captures human imagination perhaps more than any other aspect of time's nature. Is time travel possible? Let's start with the most straightforward answer. Yes, time travel is possible, and you're doing it right now. You're traveling into the future at a rate of 1 second per second, moving forward through time as inexorably as you move through space, though with far less control over direction. This might seem like a trite observation, but it's worth stating clearly. Time travel to the future is not only possible but unavoidable. You cannot help but move from present into future, each moment succeeding the last. But what about traveling into the future faster than normal, skipping ahead years or decades in moments? This too is possible, achievable through the time dilation we explored earlier. If you were to travel very fast, approaching the speed of light, or spend time in a very strong gravitational field, you would experience less elapsed proper time than someone who remained at rest. When you return to them, you would have aged less, effectively having traveled into what is their future but your near present. This kind of time travel is real, proven by experiments with atomic clocks and particles. It's not speculative or theoretical. It's an established consequence of special and general relativity, limited only by the practical difficulties of accelerating to speeds approaching light speed or accessing extremely strong gravitational fields. In principle, someone could travel to Earth's far future by journeying near light speed and returning. From their perspective, the journey might take only a few years. From Earth's perspective, centuries might pass. They would emerge into Earth's future having barely aged. But this is time travel in only one direction, toward the future. The far more intriguing and problematic question is whether travel into the past is possible, whether you could journey backward in time to visit yesterday or last year or ancient Rome. The answer here is much more uncertain. General relativity, surprisingly, doesn't explicitly forbid past-directed time travel. The mathematics of curved spacetime allows for solutions called closed time-like curves, paths through spacetime that loop back on themselves, returning to the same moment from which they started. If you could follow such a path, you would return to your own past, meeting yourself before you departed, potentially creating all sorts of paradoxes. The most famous of these paradoxes is the grandfather paradox. Imagine you travel back in time and prevent your grandfather from meeting your grandmother. Then you would never be born. But if you were never born, you couldn't travel back to prevent their meeting. The situation is logically contradictory, apparently impossible. Some physicists suggest that closed time-like curves might be self-consistent, that the universe wouldn't allow you to create paradoxes. If you tried to shoot your grandfather, your gun would jam, or you'd miss, or something else would prevent the paradoxical outcome. The past is fixed, unchangeable, and any time travel into it must be consistent with what already happened. In this view, if you travel to the past, you were always part of that past. There's no changing timeline, only one consistent history that includes your time travel. Others suggest that time travel to the past might create branching timelines, new parallel universes where different outcomes occur. You could prevent your grandfather's meeting in a new timeline, but this wouldn't affect the original timeline where you were born. This many worlds interpretation, borrowed from one way of thinking about quantum mechanics, allows for time travel without paradoxes by multiplying universes. Still, others believe closed time-like curves, while mathematically possible solutions to general relativity's equations, might be physically impossible to create or traverse. Perhaps quantum effects, unknown in Einstein's classical theory, prevent their formation. Perhaps the energy requirements are impossibly high. Perhaps there's a chronology protection principle, as Stephen Hawking half-seriously suggested, that prevents the universe from allowing closed time-like curves. The most commonly discussed potential mechanism for time travel involves wormholes, hypothetical shortcuts through space-time connecting distant regions. If you could create and stabilize a wormhole, one opening might be at one location in time, the other opening at a different location in time. By passing through the wormhole, you could effectively travel faster than light or, potentially, backward in time. But creating a traversable wormhole requires exotic matter with negative energy density, something we've never observed and might not even exist. Stabilizing a wormhole against collapse requires energies that might be impossible to obtain. Even if you could create one, using it for time travel requires carefully manipulating one opening using time dilation effects, a process that might take longer than the time travel would save. The bottom line is this: we don't know whether past-directed time travel is possible. General relativity doesn't forbid it outright, but it doesn't make it easy either. Quantum mechanics might add additional constraints we don't yet understand. The paradoxes time travel creates might be resolvable through self-consistency or many worlds, or they might indicate that time travel is impossible. What we can say is that no one has demonstrated a practical method for traveling to the past. No one has built a time machine. No one has shown that closed time-like curves actually exist in our universe, though they exist as mathematical solutions to relativistic equations. Time travel to the past remains, for now, science fiction rather than science fact. And yet, thinking about time travel, even if it's impossible, serves a purpose. It helps us understand time's nature more deeply. The paradoxes reveal assumptions we make about causation, about the relationship between cause and effect. The physics of time dilation and wormholes clarifies how time works in relativity. The very question of whether you could visit your own past forces you to think carefully about what it means for events to be ordered in time. As you rest here peacefully, breathing slowly, consider that even if you can't travel to the past, you carry it with you in memory. Your past exists in your neurons, encoded in synaptic connections, available for recall and reflection. And while you can't visit the future until it becomes present, you can imagine it, plan for it, influence what it will be through your choices now. You're always moving forward through time, yes, but that forward motion gives you power, the power to shape what comes next, to create meaning and beauty in your journey from past toward future. Time travel might remain forever beyond reach, or it might someday become possible in ways we can't currently imagine. But either way, you have the time you're given, the moments you experience, and that's enough. It has to be enough because it's what you have. And it's wonderful, this gift of time, this opportunity to exist, to experience, to participate in the universe's unfolding story. The mystery and beauty of time. We've traveled far in our exploration of time, from the fundamental physics of space-time to relativity's flexible temporal flow, from quantum mysteries to cosmic scales, from entropy's arrow to time perception in the brain. We've considered block universes and growing blocks, GPS satellites and gravitational time dilation, flow states and memory formation, the age of the cosmos and the possibility of time travel. And yet, for all this knowledge, all these insights that physics and neuroscience provide, time remains profoundly mysterious. We still don't fully understand what time is at the most fundamental level. Is it a basic feature of reality, as fundamental as space and matter, or does it emerge from something more basic? Is the flow of time real? Or is it an illusion created by consciousness? Does the future exist yet? Or is it genuinely open and undetermined? Why did the universe start with such low entropy, setting time's arrow? Can we truly reconcile quantum mechanics with relativity to create a consistent theory of quantum gravity that properly handles time? These questions remain open, actively debated by physicists and philosophers. And that's beautiful. It means reality exceeds our current understanding, that there are still mysteries to solve, discoveries to make, insights to gain. The universe hasn't revealed all its secrets, and time is among the deepest and most intriguing of the secrets yet remaining. Different cultures throughout history have conceived of time in remarkably different ways. Ancient Greeks distinguished chronos, chronological time, measured time, clock time, from kairos, the qualitative experience of the right moment, the opportune time for action. Some cultures view time as cyclical, seasons and generations repeating in endless rhythms. Others see it as linear, progressing from creation toward apocalypse or simply extending infinitely in both directions. Some traditions emphasize the eternal now, the timeless present moment that always is, while others focus on time's passage, its role in change and growth and decay. These different cultural conceptions aren't wrong simply because they differ from modern physics. They're different ways of relating to time, different emphases on different aspects of temporal experience. Modern physics gives us certain objective truths about time's structure, but it doesn't exhaust time's meaning or significance. The subjective experience of time, the feeling of duration, the sense of past and future, the awareness of mortality, the appreciation of moments both fleeting and eternal, these remain deeply personal and cultural, shaped by context and perspective and individual consciousness. And consciousness itself remains mysterious in its relationship to time. How does the brain's processing of information create the feeling of existing in a flowing present? Why does consciousness seem to have a direction, moving from past through present toward future, when the fundamental physics seems time-symmetric? Is consciousness itself creating the flow of time, or merely experiencing a flow that would exist regardless? Some philosophers and scientists suggest that consciousness and time might be deeply connected, that perhaps you can't have one without the other. Consciousness requires change, and change requires time. But time, as we experience it, seems to require consciousness to create the distinction between past, present, and future, to create memory and anticipation, to create the flowing now that we all experience so vividly. There's something deeply peaceful about accepting time's mystery rather than being frustrated by it. You don't need to fully understand time to live in it, to experience it, to create meaning within it. The fact that time remains partly mysterious doesn't diminish its reality or importance. If anything, it enhances it, reminding you that existence is richer than any complete theory could capture, that there's always more to discover, always deeper to go. As you rest here, breathing gently, let yourself appreciate time in all its aspects. The physical time of relativity and quantum mechanics, the cosmic time of the universe's evolution, the biological time of your body's rhythms, the psychological time of your consciousness, the cultural time of your society's calendars and clocks, the personal time of your individual life's narrative. All these times are real, all are aspects of the grand mystery we call time. You're a temporal being, existing in time, shaped by time, experiencing time's passage. Your birth was a beginning in time. Your death will be an ending in time. Between these boundaries, you have your lifetime, your allotted span of moments, your opportunities to experience and act and create and love and learn and grow. This is your time, unique to you, unrepeatable, precious beyond measure. The universe is vastly old compared to your lifespan, and it will continue vastly longer after you're gone. The stars will shine long after your last breath. The universe will evolve through transformations you can't witness. But right now, in this moment, you exist. You're aware. You're experiencing time's passage. You're part of the universe becoming conscious of itself, matter organized into patterns that can think and feel and wonder about time's nature. This is an extraordinary privilege, a cosmic gift. You get to be here, now, aware, experiencing this slice of space-time, this moment in the universe's long story. You get to wonder about time, to learn about entropy and relativity, to feel moments both fleeting and eternal, to create memories that will last your lifetime and beyond in the minds of those you touch. Time is limited for you as an individual. Your personal time has boundaries. This finitude is what makes moments precious, what gives urgency to love and creativity, what makes the present matter. If you had infinite time, no moment would be special, no choice would have weight. Nothing would matter because there would always be more time later. But you don't have infinite time. You have the time you have, and that scarcity creates value, creates meaning, creates the imperative to live fully in the moments you're given. And yet, from the perspective of the block universe, if that view is correct, your life is eternal. Every moment you experience exists timelessly in the four-dimensional structure of space-time. Every joy you've felt, every insight you've had, every connection you've made, all of these are permanent features of reality, as eternal as anything can be. Your life is a thread in the tapestry of space-time, beautiful and complete, meaningful and real. Whether the block universe view is correct, or whether the growing block is a better metaphor, or whether some other understanding proves true, your life matters. Your experiences are real. Your choices make a difference. The time you're given is valuable beyond measure, not despite its limitations, but because of them. As we come gently toward the end of our journey through time's physics and philosophy, let yourself settle even deeper into relaxation, into peace, into acceptance. Time is mysterious and beautiful, structured and flowing, cosmic and personal, physical and experiential. It's all of these things and more. A grand mystery that science illuminates but doesn't fully solve. A profound feature of reality that you experience intimately every moment of your existence. You are time's child, born into its flow, living within its structures, experiencing its passage in every breath you take. You're also time's observer, the universe's way of becoming aware of time's nature, of asking questions about duration and causation, entropy and eternity. You're both subject to time and conscious of it, both limited by it and liberated by it. In your remaining time, however long or short it may be, you have the opportunity to create meaning, to forge connections, to experience beauty, to learn and grow and love. Time gives you this opportunity by giving structure to existence, by creating the possibility of change, by allowing causes to have effects, by enabling memory and anticipation, by making stories possible. Your life is a story in time, with a beginning and middle and eventual ending, with characters and challenges and moments of triumph and despair, with narrative arcs that give meaning to the succession of events you experience. This story is uniquely yours, shaped by your choices and circumstances, embedded in your particular world line through space-time. And right now, in this gentle moment of rest and reflection, you're pausing in that story, taking time to consider time itself, to marvel at its mysteries, to appreciate its role in your existence. This pause, this moment of calm contemplation, is part of your story too. a chapter of rest and wonder and peaceful acceptance of time's nature. As you continue breathing slowly, deeply, letting each breath carry away more tension, more worry, more of whatever burdens you might be carrying, know that time continues flowing, moments succeeding moments, but there's no rush. Time will still be here when you're ready to engage with it more actively. For now, you can simply rest in time's flow, letting it carry you gently, peacefully, toward sleep or toward the next waking moment, whichever comes first. Time is patient. Time allows for rest, for sleep, for restoration. Your body knows this, knows how to surrender to time's rhythms, how to let go into the flowing present, how to trust that the future will arrive when it arrives, and that right now, all you need to do is be here, breathing, existing, experiencing this moment that is neither past nor future but simply now. The physics of time reveals a universe far stranger and more wonderful than everyday experience suggests. Time is not what it seems, not the simple, universal, absolute metronome we once thought it was. This flexible, relative, mysterious, profound, woven into the fabric of reality in ways we're still discovering, still trying to understand. And yet, despite all its mysteries, time is also utterly familiar, the very medium of your existence, the structure within which your life unfolds. You live in time, move through time, are shaped by time, and yet somehow transcend time through consciousness, through the ability to remember past and imagine future while experiencing present. You are both temporal and eternal, both limited by time's boundaries and unlimited in your ability to reflect on time's nature, to find meaning within its structures, to create something beautiful and significant in the moments you're given. This is the ultimate relaxing fact about time. It holds you, carries you, provides the structure for your existence, and asks nothing of you except that you be here, now, experiencing it, living it, making of it what you can. Time is both your constraint and your opportunity, both your limitation and your liberation. It is, in the end, simply the way reality is, the fundamental structure of existence as we know it. And you, resting here peacefully, breathing slowly, are part of that structure, a beautiful, conscious, aware part of the universe experiencing time's passage, wondering at time's mysteries, finding peace in time's embrace. If you'd like to support Deep Science Sleep and help us create more calming, educational content like this, please consider clicking the like button and subscribing to our channel. Your support helps us continue bringing you these peaceful explorations of science's most beautiful mysteries. Until next time, rest well, sleep deeply, and may your dreams be filled with wonder at the strange and beautiful universe we inhabit.